Okay, let's, I think it's time for us to start the morning session. The first talk is going to be given by Professor Tao Han from University of Pittsburgh. And Tao Han is well known for collider physics. So I am sure most of you know him. And he is currently the distinguished professor at the University of Pittsburgh, and also was the former chairman of the DPF. So let's welcome.
Thank you. Thank you, Hongjian.
He will give you an overview on future collider.
Yeah, it's really a great pleasure to be here in such a fantastic, wonderful the conference, and very broad, and certainly we learned from each other and learn a lot. And so for this particle physics group, I was asked to give an overview on theoretical motivations for our future, in particular for future collider. I would like to first echo that Ed Wheaton stated during the panel discussion. And of course, we have many ways to make progress to understand particle physics to deeper level. And of course, from the two major frontiers, one is that we want to do the precision measurements and better understand nature, understand our standard model to a better level. But the other one is that we want to go to the energy frontier to explore shorter and shorter distances and probably produce new states and new interactions. And Ed Wheaton basically said it is a high energy frontier in terms of collider. Future collider is indispensable. That this is basically in accordance to my discussions here, in particular for theoretical motivation for future colliders. So let's move on to see. Oh, by the way, so then. So we are all here at this beautiful area. This is the Yanxi Lake. So then here is the Sunrise Building, very impressive. But the other one is in contrast, we have a lot of water there as well. Rivers, but not lakes, 3 rivers. This is the Pittsburgh downtown. So some of you may not have been through there, but so welcome to visit us. So let's go on to see what happens. I think this is a fair statement that we have made so much progress and we have enjoyed the uninterrupted discoveries in particle physics for many decades. Okay, so in particular, if you think back, so more than almost like 60, 70 years, if you go back to the early standard model construction, and from quarks, think about if the quarks are the fundamental ingredients constructed in our standard model, and then from quarks and on to complete the standard model particle spectrum, from quarks to the Higgs boson, this is really heroic efforts in theory and experiments. So this is our standard model particle spectrum in the 60s. We have this the construction of the quark model and also the observation for the proton substructure, and continue on for 70s to discover the heavy quarks and the charm, and also tau particle, and continue on for the 80s. We discussed directly observe the mediators like a W and Z spin 1 gate bosons, and further on we find the last the heavy quark, top quark, and of course, not mentioning about the in-between, we understand the structure of standard model, including the flavor physics, and we observe the neutrino states. And finally, we observe the neutrino oscillation, and only until 2012, that was the last piece in the standard model construction in the Higgs boson at the Large Hadron Collider at the CERN. So this is my statement to say that we have accomplished so much. It's uninterrupted discoveries. So continues. So this would make John happy that John basically made this up for this the T-shirt. And so then you can see that in terms of our understanding of the structure, you can cast this into such a compact structure, of course. So then this is quite a triumph for us. The statement is that the standard model, as it is the most precise theory not only in physics but in science overall. So this is the first one you have been able to reach such a high level of consistency and accuracy. So this is the correct statement to say that all the properties we need to have a complete theory to describe our macroscopic world: quantum mechanical, relativistic, the unitary and finite, and renormalizable, and vacuum basically stable, and it is applicable to an exponentially high scale. Could be even as high as a Planck scale. So basically, this structure has this self-consistency, both in terms of mathematics, in terms of physical need, and all these fundamental properties. This is the most accurate level. So in the sense that to extend the John put together to include everything, including pretty much everything. So here we have a quantum mechanical path integral to sum over all these quantum states, and we have the metric to describe this the space-time, and we have the gravity here, and the gauge field, and the fermions, and the Yukawa interaction with the vacuum background. The vacuum background is described by scalars like Higgs. Everything is pretty much here. So this is all about fundamental particle physics, pretty much on one line, including gravity, not quite a quantum yet. So therefore, there is such a bold statement. Eminent physicists made this remark. Most of the grand underlying principles have been formally established. Okay, period. And the future, well, the future is just the details and look into the sixth place for decimals. So this sounds like almost consistent with what I said in the previous slides. And of course, and this also sounds like a statement from a really arrogant theoretical physicist, probably. Who said that, actually? It's Albert Michelson in 1894. So, you think that would be the case? In fact, the reason he said that is that everything seemed to be more or less in place, and he carried out the experiment to search for ether, did not find it, and but did not seem to be a big deal. However, you see, the non-existence of a certain observation may still tell us some fundamental principles. So the non-existence of ether, to go against this relativity description, is really the moving off point for modern physics. Of course, the general relativity aspect. So if we repeat this, to think about this probably is a little bit too ambitious to think that we have done with everything. So this is certainly the first warning to all of us, to the audience, and that there are significant aspects, in particular even from theoretical aspect, that we should look into to think about the future possible discoveries. So, whether Higgs will repeat itself at this current situation, we mathematically and theoretically we have this sort of consistent theory, but it does not really necessarily mean everything. Now let me pose a few questions. This I don't mean to discover what particular particle interaction. Let's ask our fundamental questions. How much we have understood the standard model in terms of physical aspect. So let's first question: how much we understand the electric the vacuum state, the current vacuum state around Higgs? How much we know? In fact, if we adopt this the Big Bang cosmology, think about this early universe. At a short time or at a long time, 10 to minus 9 seconds or so, as the universe was as cold as 10 to the 15 Kelvin, it went through a phase transition. That is the electroweak phase transition. So that electroweak phase transition took place and lasted until now. We are living in this the broken phase, basically. So that basically means that somewhere you have this the symmetric. You have a symmetric, You have a symmetric potential, and due to the temperature dependence, and then developed into a new vacuum state, lowest energy state in this particular region. And that's of course in the standard model is parameterized by this simple form. If you look at this simple form, for most of us who learns about the superconductivity, it's very similar to the Landau-Ginzburg parameterization. Landau-Ginzburg parameterization has an identical form like this. The order parameters, the phi squared, and the other one, the phi to the fourth, and with the temperature dependent coefficients like this. When the temperature cools down lower and lower, then this constant alpha becomes negative, and therefore you develop the non-zero vacuum expectation value. That from the alpha to be larger than zero to alpha to be smaller than zero, it underwent the so-called phase transition. So, to some extent, you think the standard model is nothing but a Landau-Ginzburg parameterization. That's not true at all. The reason is that Landau-Ginzburg is the only effective phenomenological parameterization. It's really parameterize this as a order parameter to describe the vacuum value, vacuum expectation value, rather than anything more dynamical. The more dynamical aspect is BCS theory. Barton Cooper and Schrieffer, they developed the underlying interactive theory to form Cooper pair, and so on and so forth, and a vacuum condensation for the Cooper pair, and develop this into this the vacuum non-zero vacuum expectation value to have this feature. But in the standard model, we have this relativistic field theory. It's not parameter. This is a phi field. It's a field. It's a dynamic field. It's a relativistic field. So it's not the same at all. It is not a Landau-Ginzburg in many aspects. So in a sense, for example, the Higgs sector here contains these two terms that we know from the current experiments at the LHC and the particle physics measurements. So ever since the beta decay was observed, you know that there is a short range mediation. So therefore, then from the beta decay, the G Fermi constant immediately gave you the order parameter already. So even back in the 30s, we more or less know there's a new scale. So that is more or less we know already. And then now we discover this the Higgs scalar at 125 GeV, putting all these constants into your framework here, into this framework. Standard model is fixed. No, in the electric sector, no free parameter anymore. So therefore, you can see the properties. You see the properties, and if you look at this potential, you go through this phase transition. This is almost not sharp phase transition at all. It's not only not first order. It's even hard to tell this second order. It's kind of a crossover shift from one phase to the other phase, unlike the other thing. And you calculate the penetration length, and which is proportional to W mass, and the coherence length is proportional to the coupling, effective coupling, the Higgs boson. And this is the type 2 electroweak superconductivity in general. But it's very different from the other type 1, other typical situations. But in particular, this coupling from the Higgs mass measurement is determined to be very small. This is weakly coupled theory. Normally, dimensionless weakly coupled theory, we always call the new force. Right? Just like electromagnetic force and electroweak force. But this could be viewed as a new dimensionless, new interaction, weakly coupled force. I think it's fair to call this a fifth force. We should have seen this new force. But then also, if you compare the decay width and the Higgs mass, that is tells you the resonance. The resonance, the width is 10 to minus 4, 10 to minus 5 is extremely narrow. Very narrow, weakly coupled particle standing there. Nothing exists like this in our superconductivity. In our normally dynamically interacting systems, like a QCD and so on and so forth. This is new. To some extent, this parameterization is far beyond the Landau-Ginzburg. This Higgs itself is new physics. Higgs itself is new physics. We don't understand. It never happened before. You must understand Higgs to the deeper level. Okay. So in that case, we want to have a deeper level to calculate these parameters, such as the BCS can do. BCS can do these calculations for any given system. Given system, you use the normal procedure. You can calculate the coefficients more or less, and then you know the superconductivity properties. But here, the sole turnout for any underlying thing you want to do, you get into trouble. Let's go through some of the troubles. Let's look at the first term. How do we calculate understand this mass term to a deeper level rather than simple parameter? Now, if you want to use this general argument, like this is the effective field theory and coming from a more underlying theory, the best way to describe this the so-called effective field theory formulated by Ken Wilson, right? So Ken Wilson would say, let's write down all the operators according to the operator product expansion, and then we have the dimension 4. We call this a marginal. In a higher dimension, the operators will be smaller effect. We call this irrelevant operators because they are small suppressed by the power. But the higher dimension, the lower dimension operators, before dimension 4, dimension 2. Dimension 2 will be the relevant ones according to Wilson. The relevant ones, the first relevant one would be the first term. The first term actually is lambda to the 4th. That's the cosmological constant. We don't know why this cosmological constant, most relevant operator, actually is almost 0. We don't understand. Now the second one is the lambda to the second power. Lambda to the second power is basically the only dimension 4 constant mu squared. It comes from in your potential give the Higgs mass, but it's still so much smaller than this one. So pretty much in any theoretical calculations, given an underlying model, given a theory, supersymmetry, technical, give me anything, and you calculate, you always encounter these the large quadratic corrections to the Higgs mass. That's because Ken Wilson observed this even in 1970. Ken Wilson said that a scalar like this has no particular symmetry to protect the mass. All these new contributions add up. It's additive. If you have additive two terms, then you have subtraction. Then addition is a subtraction. You have a huge cancellation in between these. And we call this hierarchy fine-tune, right? Because we haven't seen the new scale. The new scale goes all the way. We even argue possibly to be as high as a Planck scale. Then how do we do the additive terms to give you electroweak scale, and unlike the mass corrections? The other mass corrections, such as the W mass, it's a gate boson. And the gate symmetry, when the gate symmetry is exact near the breaking, before breaking, then the mass correction is multiplied by this. So therefore, it's a symmetry protection. Fermions are similar. Fermions have this chiral symmetry, and chiral symmetry protect these large corrections. So it's a multiplicable. It's rather than additive. So Higgs is the only one that we don't understand. That's why we said Higgs is something we need to understand better. They give you some problem now already. It gives you some problem for the new dynamics. So the new dynamics, either you need to introduce a new symmetry such as supersymmetry and maybe dynamical symmetry and so on and so forth. We need to understand why the Higgs mass is in such a sensitive connection to the next scale. So otherwise, we don't want to. I hope not to give up to use this anthropic principle to say this so happens just like a cosmological constant. I think that's so far we don't want to give up. So far, I don't think that's scientific enough. So we really want to understand the underlying dynamics. Okay, let's look at the second term in the Higgs potential. The first term is troublesome for the mass correction. Second term is about the interaction, the coefficient. This coefficient, as I mentioned to you, is a new dimensionless, weakly coupled theory. So that's from the LIC. But this also gives us some problem in connection with any new theory already, such as supersymmetry. Supersymmetry is an elegant theory to introduce additional symmetry, space-time symmetry. In the largest symmetry in the S matrix in the field theory construction. However, if you make the supersymmetrical connection between our gate couplings and also the scalar is due to symmetry, scalar is a symmetry with the fermions, and then you see that this prediction is not quite right. So this prediction is a little bit too small because of a large Higgs mass here. And then even you introduce a tree level. This is a tree level. Yeah. Yeah, but the point is that if you want to make a connection with the new measurements, the new measurement is from the Higgs mass extraction. You extract, you know, I'm sure you know, we know the same story. If you simply use the supersymmetrical parameters to calculate Higgs mass and drag the Higgs mass, you wrote one of the first papers. Otherwise, below the Z mass. You need to drag the Higgs mass to be above Z due to the quantum corrections. You need to have the stop and large mixing to drag this to this value. This is what I was trying to say. I was trying to say that the supersymmetry would drag your Higgs mass to a high need to. Well, so let me repeat to see whether I can make this clear. This is so-called a little hierarchy. The little hierarchy basically means that if you use the current Higgs mass determination, you need you need to have a relatively significant contribution from star, but we haven't seen that yet. So it's not the current observation, both non-existent supersymmetry particles and the large Higgs mass. So here is this is the large the so-called the little hierarchy problem. So here, what I was trying to say is that for any given theory, including a composite theory or you use the supersymmetry, the non-existence push this into a little hierarchy problem. So that's what I was trying to say. I don't know whether I made this make this clear. So we can come back to argue about this the terminology and to make the picture. What I want to say to summarize that from the current measurements from the Higgs mass, this is the fixed, and this gives you a significant constraints, inconsistent. It's not convenient situation when you introduce a new TeV scale new physics here. So these are the two things, and nature about electric symmetry breaking. We understand the electric symmetry breaking according to the Higgs. If that is the case, then that basically means that we measured two quantities. One is the Fermi constant. It tells you the vacuum expectation value to how far away from that. And the second term is we measure the first derivative. The first derivative is come from the Higgs mass. But how confident we think that we know the Higgs potential just like these two terms? According to Wilsonian, you will be able to have some additional contributions related to the heavy new scale lambda, dimension 6 operators, or if you sum over these contributions, you may even form some additional formalism like this the Coleman-Weinberg logarithmic potential. So how much we really know the shape of the Higgs potential? We only know two terms, the first two terms. So any higher order corrections and also the possible resum, the corrections may lead you a significant modification beyond the standard model for the triple coupling, which is not measured yet. These interactions so far has not been independently measured yet. Only thing we know is to measure the mass to extrapolate its quantity, lambda. But we don't know the triple coupling yet. But this triple coupling may change your standard model value by order 1. That will have a significant impact for the shape, for the potential, therefore significant impact on these early universe cosmologies such as the electric phase transition. So that will be very, very interesting and important. Otherwise, we only have a crossover slow transition from one vacuum to the other, then there's no significant dramatic physics such as electric baryogenesis and so on and so forth. So we need to do this in a more precise way. So this is again the very strong motivation to explore the terms interactions possibly beyond the Higgs potential and trying to understand how this phase transition took place. So that is a very important aspect. Okay, so far I only list the two prominent examples around the Higgs potential. It's an absolutely important question we need to answer, and the questions can continue to be listed, such as whether the electroweak interaction can be combined into a larger interaction sector, such as the grand unification with a strong interaction. Or maybe we have the space-time symmetry extension to introduce a supersymmetry so that we predict new interactions, new spectrum, new particle spectrum, and therefore very rich new physics. And what about the cosmological inflation? This is basically cosmological evolution and dark energy and inflation and so on and so forth, whether they play any role with scalars, with a Higgs potential. And eventually, we want to understand the quantum gravity when we reach the Planck scale, right? Maybe string theory will give us the guidance and so forth. Okay. Now, so those are the questions, the motivations are all there. We want to further explore. Let me ask 2 or 3 more questions. These 3 more questions are from observational aspect, but it's necessary to have a solution. Okay. The first one is about neutrino mass. In the simplest standard model construction, neutrinos are purely left-handed, no right-handed neutrino state, as Weinberg constructed theory, and we know that it's incomplete because we have observed the neutral oscillation the phenomena, and therefore neutrinos are massive. So in that case, you have to extend. So how many neutrinos you want to do the extension? Well, 3 left-handed plus right-handed. So you can construct the Dirac mass, or maybe that's not the right-handed state may even give you some additional features such as the Majorana like. So it's also very important. And in particular, it may help you to understand the smallness of neutrino mass with respect to the other particle spectrum. Okay, then whether neutrino sector is very rich, like the quark sector, to have additional CP phase, and whether this is the first chance to have this the stereo neutrino, because the right-hand neutrino has no any other gate quantum numbers. This is the only one you could contemplate on this neutrino is Majorana-like, and maybe this neutrino is so neutral. Therefore, it may have the best chance to talk to the dark sector beyond the standard model, and so on and so forth. So neutrino physics is very rich. Neutrino physics will continue to provide deep knowledge for us. And neutrino studies have led more discoveries, more Nobel Prizes than any other subject. So if you, not even counting Pauli and Fermi. So even in the recent cosmological and astronomical and particle physics observations, neutrino physics will remain to be a very rich place to explore. Okay. So then it's both the theory and experiments allowed to do. So determining the natures and the mass and generation mechanism is likely to have a revolutionary new directions to get into. So along the same line, the neutrino physics is related to our flavor physics, as we said. In fact, I gave a talk at IHAP Monday. I mentioned that the muon neutrino observation from this the Letterman's experiment at Brookhaven was beginning to define the flavor physics. That was even before Kabibou mixing. So then the muon flavor was observed different from electron flavor because there was no electron now kicking out. I would think that is the first time you can identify a different quantum number between two leptons. So then in that case, we generalize this into the quark sector. You see that the quark sector has this mass difference like from the largest, the animal top quark, that's the whale. And then you continue on to a smaller one, the 3 orders of magnitude below, and you go on for another 3 orders of magnitude below. And that's pretty much all the particles. And then you want to say that everything is proportional to the Higgs wave. All the particles in the standard model, including the very light fermions and very heavy top, and all the way down to the neutrino sub-electron volts in that. It's not even quite the same as the other animals. It's as small as mosquitoes. How much the confidence we have, we say that everything is coming from single value, vacuum expectation value. You think you really believe that all the other animals, including such small insects, coming from the same mass generation mechanisms? I think it's a little bit too ambitious to make the claim. So I think something maybe just like the seesaw mechanism or some new scale will come into play and then give you some fit. I think overall that the flavor physics is very pressing, and I think that flavor physics is one of the major motivations that we have to look into to think about physics beyond standard model. Okay. The second one is another one. Most time we call this most wanted. So the dark matter we know does not exist in the standard model, called dark matter. And then we know dark matter exists. And the good news is that we do have ideas. We do have theoretical formulations for the dark matter candidate as well as the dark matter mass. However, it becomes embarrassment because we don't know the mass range anywhere it's possible. You can even have this the orders of order magnitude from all the way from the very light wave-like axions, dark photons, and somewhere in between neutrinos, maybe several neutrinos, move on to the favorite one that the electroweak scale, we call electroweak, weakly interacting massive particles, and then all the way to very heavy grand unified scale, and even possible primordial black holes. So they're all possible to serve as some kind of a cold dark matter. So then we have to really explore everywhere. We want to do the direct detection from the from direct detection for underground experiment to see the dark matter flying by and to kick the materials, and then maybe from the indirect detection from galaxies and the center of the our galaxy and so on and so forth, and eventually to see whether we can produce weakly interacting dark matter at the colliders. So that's that gave us all the opportunities to explore the dark matter domain. But this once again is most wanted the piece we need to look into, and hopefully it may lead to the next discovery for this for the physics beyond standard model. So the last one I want to say is that our existence is evidence for physics beyond standard model, because we don't have enough CP violation, we don't have enough Baron number violation. We need to put them into the systematic framework. So therefore, the baryogenesis is a necessary mechanism to explain our existence, and that is necessary for some physics beyond standard model. Then, once again, many ideas that want to satisfy these three conditions to generate our existence. We need to have the Barrow number violation, which may be okay from the electroweak transition. We need to have a CPA violation, but we don't have enough CPA violation in the quark sector. And then we want to have this to take place out of equilibrium, which we don't have that in the Higgs sector as well, because I mentioned to you this only very slow crossover for the transition. So this is a clear evidence something else need to be taken into account in order to understand that. But once again, we have a lot of theoretical motivations for this. We have a theoretical formulation as well. High scale primordial, the primordial universe will probably be able to utilize the Affleck-Dine mechanism. And laboratory analysis, laboratory number violation may be associated with the Maranello neutrino, and maybe at the electroweak scale for the phase transition is responsible for this Barrow number violation. So you see a lot of interesting theoretical formulations that can utilize these and to materialize the Barrow number violation, but certainly it is necessary to look everywhere to see the proton decay, to see the neutron, anti-neutron isolation, maybe Maranello neutrino surge, and additional Higgs sector, and gravitational wave, so and so on and so forth. So it's this once again very rich. I think how much time I have? I think the theory part is more or less done. The next part was to see how much. Oh, I still have a lot of time. Oh, that's good. Well, thank you for your generosity. So now we want to see what are the opportunities, the chances we want to follow up the theoretical ideas, the theoretical motivations, so that we can make progress in the hope to have the next discovery. So of course, in the US, we went through quite a few years. So we were thinking to do this in 1 year, but because of pandemic and so on and so forth, and we went through this so-called community summer study, and supposed to conclude in 2021. But at the very end, we conclude this in 2022. And the major summary conference took place in Seattle, and 2 years ago in the summer. And then we basically had an order for 700 physicists worldwide, and not only the U.S. was led by the U.S. APS DPF, but it's really a global activity to put all these physics together to see what may be our next targets, opportunities we should move on. And as a summary, and the panel, the P5 panel came up and to summarize our physics input and decide what may be the priority in connection with the available opportunities, including funding profiles. So that is the so-called P5 report is written here. It's a very lengthy report, include all the physics and also the recommendations. So that is at the very end, it came into such a very nice picture to say that we discovered the Higgs boson and understand electroweak sector in the standard model up to 100 GeV, and now the LHC continues. We understand around the 1 TeV region already, and we certainly want to continue to explore. The LHC will be our lifetime the investment for the next 15 or 10 to 15 years for sure. So then, of course, neutrino is a very light, very small, that all come together into this the deep, small-scale quantum regime. So this is what definitely we want to continue on to understand nature to shorter distances. On the other hand, in the larger distance, we see the mystery and puzzle already, right? We see the cosmological evolution. We don't know what's the drive. What is the driver? Cosmology constant, or this is the time dependent the evolution of the field. That was also prominently discussed in the panel 2 days ago, and by our string theorists as well as cosmologists. So certainly we want to understand the dark energy and the possible identification of dark matter in this even in our observable world around us. We want to explore, illuminate the hidden universe, and somewhere between. So then we have a short distance and long distance, but then we somewhere between we have this the quantum regime, and then we want to explore the precision physics and including the cosmology and collider research in somewhere in between, and so on and so forth. You can see that all these the pictures come together, and we have a coherent the understanding of the structure and so on and so forth. So opportunities, LIC, as I mentioned to you already, LIC is going to be our the major enterprise for a long time to come. We have to utilize, we have to make the LIC experiment fully successful. Okay. So far it's extremely impressive already. So then, so for the moment, I think the LIC run 3 started already, and we hope to accumulate all of 300 from the luminosity. It's roughly factor 2 or so more than what we have now. But then there will be shut down to significantly upgrade into the HL, the high luminosity version of the LIC. So that's so then somewhere in between 2027 also we have a 2-year shutdown to improve the luminosity by almost like another order of magnitude. Think about another order of magnitude. That means we only have 10% of the LIC luminosity. We're going to have another almost order of magnitude luminosity to play with. So we are extremely hopeful to see the physical potential to have something beyond what we see. So it's not time to be disappointed with the non-existence for anything beyond Higgs yet. Okay, so it's a long effort, and we should all try to understand the LIC search potential, understand the standard model background, and understand the processes, and in the hope to optimize the outcome from LIC. So that is going to be our first priority. Just give you some estimate. We need to understand the Higgs sector, and also in connection with the early universe cosmology, right? We argued about the importance of this electric phase transition. And I mentioned to you already, the triple coupling is the first one to have direct impact on the shape of the Higgs potential, and that is one we haven't seen we haven't measured that yet at LIC. But unfortunately, the LIC energy is still not quite high enough, and the background is still a little too large to extract the information. You may be able to reach something like a 50% accuracy for the Higgs triple coupling. It may not be conclusive. It would be good to see the non-zero triple coupling already, but it's not conclusive to say standard model is correct. Therefore, it's a crossover. Not quite yet. So we need to continue on to carry on the project beyond the high luminosity LIC, even for the sake to understand the Higgs potential, that sector. Then, of course, the new physics that I mentioned to you, according to the Wilsonian power counting, new physics is likely to come in like a 1 over lambda squared. So then in that case, and so if you move on to the LIC energy and beyond, you are more sensitive to the new physics scale according to the lambda squared beyond a few TeV region. Okay, so the Higgs is a clear target. Higgs exists, and we should the highest priority to prepare a Higgs factory worldwide, whatever it is. My statement is any new particle discovery, there's a factory all the way back to pion factory, kaon factory, charm, tau factory, B factory, Z factory, W pair tau. Any new particle, we want to study this to death. Higgs is no exception. Higgs, my statement is the Higgs factory will be built by someone at somewhere at some time. I don't know. Higgs factory is a necessity. Okay, we must prepare a Higgs factory to study Higgs to the level that for all the other particles. That's I think that's the community basically is unified along this the party line already. Of course, we have options. The International Linear Collider in Japan, and the site was chosen already, and the study has been carried out more than 20 years. It's the most mature machine design in terms of the machine design and the detector design and the physics case. But we don't know whether the Japanese community and the government will move forward for that. And we have a lot of other options. The other one, prominent one, has been discussed for the almost 10 years here in China already. We call the circular electron-positron collider, and shoot at the threshold for the Z Higgs pair production, and that is the typical value for the Higgs factory, to have the Higgs and Z pair production in that region. And then furthermore, we could consider the 300 GeV-ish, the linear collider discussed intensively at the CERN for the past more than 10 years already. Christopher was one of the leaders. to develop this here, and we call it CLIC, the CERN Linear Collider here. And then we could lower the energy to 200 HGeV, then it's very close to the Higgs factor there already. And of course, the counterpart at the CERN, similar to CEPC, is our FCC, Future Circular Collider. And the Higgs factor is the electron positron version, but in the hope we can go beyond. But so you see a lot of options, and these options will also lead to rich physics, not only at the Higgs factory, W para threshold, Z resonance, and possible TD bar threshold, 350 eV as well. But that's not most prominently discussed. But the Higgs factor is certainly a must. So that's an opportunity. So I have some a summary plot, but I don't want to go to details. Just to give you a few points. If you compare this top, the very long bar, it's a gray color. That's how we can expect from the LHC, hydrogen monoxide LHC. But you can see that a significant improvement from the Higgs factor measurements. This is the gate boson coupling here. Then even more impressive, that the fermionic coupling. For example, the Higgs to charm. At the LHC, we just don't have the accuracy to dig out the signal from the QCD background. But the lepton colliders are so clean, and you can expect to improve this again by more than order magnitude to the percentage level. So then the percentage level is accurate enough to say the theory is basically right. And then the modification would be rather small. And finally, you can even determine the Higgs width in a model independent manner. But for the LHC, you basically put some bound. But for the lepton colliders, you're able to measure the Higgs mass in the Higgs width in the model independent manner. Just like the Z pole, you don't have additional parameters like a branching fraction or something. You can just extrapolate this thing. Lepton collider will have this capacity to measure the Higgs properties to great precision and also in a model independent way, in the hope to see the deviation. If you see a deviation, that tells you some possible indication something else beyond standard model upcoming. So that is Higgs factory. But to my heart is energy frontier. So we want to move on to the LHC and beyond. So from LHC, from Tevitron to LHC, the center mass energy is a factor of 7. Factor of 7 is order magnitude. For theorists, 7 is 10. So this, you want to move this center mass energy by 1 order magnitude. So then if you go to this, the next generation hadron collider plant, such as the SPPC is the same version as the CEPC, same tunnel, but change the magnets into the proton, the hadron colliding version. But this FCC is the same, but in the HH. So that is also the new version. So hopefully we reach this the 100 TeV center mass energy, which is once again a factor of 7 beyond the LHC. So another order magnitude. I think the 10 TeV partonic central mass energy will lead us to the next stage. So I think that's an important target. So then, of course, there are options. The hadron collider is the obvious one. But the recent interest comes into this rather demanding but brand new technology, possible the muon collider. Okay. The muon collider, of course, is very interesting in several aspects. The reason is that the muons are 200 times more massive than electrons. Very little radiation, because radiation is the energy, the mass ratio to the 4th power. You get the 100 million times improvement for the energy. The synchronous radiation saving, but the muon has such a short lifetime, microsecond, twice a microsecond lifetime. You have to manipulate the beam quality, we call the cooling, and then accelerate this in such a short time. And there is a challenge. In the last P5 in 2013, basically terminated the major effort at the Fermilab in the US because of a technological challenge. And so then this recent P5 was based on some recent improvement in 2019. 2019, and the experiments for the muon cooling at the Rutherford lab in the UK, so carried out this MAP, muon accelerator project, and it's called the MICE, muon ionization cooling project, and they demonstrate the possibility for the cooling. But this is by far not enough. This is something like 20%, 30% cooling effect, but you need 5 orders of magnitude cooling effect. You want to have high quality beams. It's a long, long way to go. But this demonstrates the cooling effect is possible in the laboratory environment. Because of that, and the community came back, and in particular the junior colleagues in the US, they got excited about this possibility. And this is an article, Scientific American said the particle physics is the dream of a muon collider. So it's even last year. So it's quite a few articles, very dominant, the important journals. So in Nature, is that US and Europe should team up for muon collider. And of course, it was all adopted by the P5 report. And P5 report emphasized not only 10 TeV partonic central mass energy, but singled out the muon, single out to say that the road toward the future collider may be at the Fermilab to think about the capacity of the high proton beam, and in the hope to do this muon collider in the future as well. And this statement really resonates our idea. We call this is our muon shot. Some of you may not immediately pick up why it's called a muon shot. That's trying to mimic the JFK in the John Kennedy statement. It's called a moon shot. So it was a major project for us, and the muon shot was trying to see. It is exciting, and so we probably should pay attention. And once again, we can repeat JFK, right? So it's not because it's easy; it's because of hard. So we want to engage some hard topics. And then, of course, it has a greater potential for all these machines. And for example, the measuring the Higgs triple coupling is very, very important. And the LHC is only marginal. You will be lucky even to see the Higgs pair production and the measure order 1 lambda coupling. But I mentioned to you, this is only 50% accuracy. But if you go to 10 times factor of 7, higher luminosity from LHC to the FCC, HH, or SPP, then you probe this the accuracy by 2 orders of magnitude. So you understand the interaction by 2 orders of magnitude in terms of 1 over lambda squared, right? So here the summary plot to see the accuracy. Here is roughly about 50% from the high luminosity, but the Higgs factor will improve somewhat, but only by the virtual. But only the loop effect, model-dependent loop effect. So that's one. And then if you are able to go beyond the Higgs factor is not placed to measure this triple coupling because of energy and precision. So the energy threshold to produce Higgs pair copiously at this the future the FCC, HH, or at the muon collider. So you will be able to, so here, this is muon collider. Then you have the order of 10% accuracy. If you measure the Higgs coupling like the standard model and a 10% accuracy, you more or less believe the standard model is correct. If the standard model is correct, it's very disappointing because the phase transition is a crossover, not much new physics during that time. That we have to find other solutions for these fundamental questions, such as bioredundancies and so on and so forth. Okay, so this is a critically important aspect. So we need to conclusively test the standard model electric phase transition in the hope to identify new physics. Of course, once you go through the 10 TeV partonic central mass energy, you open new threshold. Any new particles that easily pop up. Higgs pair, the supersymmetry particle, whatever particle cross the threshold, they all pop up. At electron collider, it's very, very easy to observe. Even think about Higgs. How easy the Higgs was discovered? We thought it was very hard. Once you go across the threshold, in a year, you discovered Higgs. So energy threshold luminosity model independent. Once you have a new physics, so you will not miss that. So that's the energy frontier is the one. Perhaps. Yeah. Yeah. Oh, yeah. Yep. Yep. Yeah. Yeah. Good. Very good. So because of time, I skipped that. And we wrote a paper to explore this complementarity for muon collider. It was a very, very important, very, very, yes. So we had a paper on the WW fusion process to produce a Higgs pair. Yes, that's definitely true. That's definitely true. So that you can see the complementarity. So I agree that that certainly is true. But in principle, you could look at the other the dimension 6 operators to contribute to the two processes. To come to dimension 4, this one is a typical one is dimension 6 operator, right? But beyond standard model physics, dimension 6. Yeah. So then yeah, so I would looking forward to see the complementarity. So that is certainly it's a very, very important, very rich physics there as well. So this I probably would say this is the strongest motivation. Other people may not agree. So this is associated with the supersymmetry, right? Supersymmetry, nevertheless, I believe supersymmetry is strongly motivated. So whether it's there or not there, we see how nature works. But in terms of the theoretical structure, and in terms of many questions I asked in the early discussion, that supersymmetry nevertheless very well motivated the structure. So then, as I mentioned, once you cross the energy threshold, the 10 TeV partonic center mass energy will give you very important information. So here is a comparison. If you think about the new particle production, it doesn't have to be totally supersymmetry, but any colored particles, you will have a very easy access by hadron colliders. So for example, this is some stop type of the color triplet particles. Then these the hadronic collisions would lead you to a very large production rate, and this is FCCHH. But however, if the dominant contribution comes from the electroweak sector, such as Giginos and Higginos, and then the hadronic production does not help you too much, and the background may overwhelm. So therefore, in that case, leptonic colliders, such as the click, 3 TeV click, and such as the muon collider, that give you immediate signature, almost like twice. The mass reach is half of the center mass energy in that region as well. Okay, so Giginos here, you can see that you immediately win over the hadronic colliders, LSC and this one. So the partonic center mass energy in different machines will also have a complementarity to move on. So then again, I scale like a 1 over lambda squared. If you have the Higgs mass precision, 1%, then you immediately move up to this new physics test by 2 orders of magnitude. So if you don't find some particles around the multi-TeV, and you square this 1 over lambda, it's 10 to the minus 4 fine-tuned. That makes us wonder whether our fine-tuned argument is really a principle to guide us. Maybe some new form. So somewhere I declare I don't want to accept the anthropic, but somewhere between maybe some new mechanism, similar to the non-existence of ether, right? Non-existence did not mean that, well, your simple velocity addition is bad, but rather some more fundamental, the speed addition, velocity addition principle comes in. Maybe we can even figure out some more fundamental principles rather than adopting this normal fine-tune. Okay. So finally, let me summarize about the dark matter direct search. Dark matter search, you have seen this kind of a direct search quite a lot. It's extremely impressive for the past decades or more. That pretty much every year or two, our experimental colleagues, the underground direct search, will be able to improve the cross-section measurements, therefore translate into the coupling strength versus a very broader range for the WIMP dark matter mass to multi-TeV and from GeV to TeV 3 orders of magnitude by order of magnitude. This is direct detection. This is most important, most direct. So this is the direct observation if you find dark matter. However, the complementarity is with the collider. If this is weakly interacting, you'll be able to produce this from weak interactions at colliders. And the colliders are so complementary that help on both ends. On the one end, here, this is low mass. Low mass because of the low momentum transfer and the insensitive kick. So the direct search detectors are much less sensitive. The dark matter is so light, does not kick this too much, and the detection is hard. But the specific collider, the lighter the missing particle is, the more missing connecting energy is, just like neutrino. Neutrinos are all the major source of missing energy. It's massless and missing kinetic energy, so that's the most striking signature for supersymmetry and for W discovery, for top quark discovery for that matter. So the missing energy, missing neutrino, is most sensitive to differentiate from the center model background. So therefore, if the dark matter is rather light at missing energy, then the collider search is a very good complementary to that. Okay? On the other hand, if you have a very heavy dark matter, then the heavy dark matter has a lower the radical density and lower cross section. So the heavy dark matter multi-TeV range becomes much less sensitive in the direct search. But this is again good place for a filter collider. You could go cross the threshold. I mentioned you once you go cross threshold, you won't miss it. Once you go across the pair production threshold, you pick it up. So multi-TeV central mass, partonic central mass energy can easily probe this up to central mass energy over 2. So both two ends for the WIMP dark matter search, this is extremely important complementarity and strongly motivated for this the filter collider search. I think that's pretty much it, and we can have some model to say, let's do some most general. I think this is the Alejandro was one of the early people to 2 minutes. Okay, I can summarize. So this is called the generalized WIMP dark matter, and so I think I quote Alejandro. Yes, I'm glad I did. So this is one of the early papers Alejandro company the formulate. I think it's a good model, good parameterization. I don't necessarily believe this is the correct theory, but this is very representative, and we have been using this as benchmark to do these the searches. And the conclusion is that when you connect this with the electroweak interactions, and we call this the generalized WIMP, so then you have some very accurate estimate what the mass should be if you identify this dark matter as a major, the dominant component of the radic. So because of that, you can have the mass target to for collider to search. And our conclusion is the future collider, multi-TeV filter collider is quite likely to fully cover this and give you a very impressive coverage for this. This is essentially Higgsino-like. This is essentially the doublet is Higgsino-like. We know it's triplet we know like, and then even beyond the higher representations. So then you can even search for this all the time anyway. So this is the numerical summary, and my comment here is that it's complementary, and for the color states, the hadron collider is good. For those the dark matter states, the hadron collider is not good. The lepton collider is better because of the threshold and the clean environment. You can see that these bars here, this is the thermal target from this estimate. So then you can see that we are able to extend to the beyond the thermal density. Let me summarize. So as we discussed, the electroweak sector is really in between at the pivotal position for physics before and physics future. Okay. Now, what I have been seeing here is that I strongly argued the electroweak sector, understanding Higgs sector, understanding the relation of the Higgs sector with many other aspects, including cosmological evolution and cosmological observations, astronomical observations, as well as the mass generation mechanisms and fundamental symmetries. I think there was ample examples that the electric sector need to be understood better. Higgs is the pivotal position. Higgs is the new physics. So then here, now we have been exploring the observable world, and then we are puzzled by the cosmological evolution such as the dark energy. And we are missing a major component as dark matter, and we need to continue to search for this. Now we are in the region that electric sector, and we seem to understand the mathematical structure of mass generation, but by far it's not enough. Flavor, neutrinos, and it's related, but it's certainly not going to explain everything. And we are shooting at the next the order of magnitude from this the future collider. And I think that this hopefully will be fruitful for us. And I think the future, the high-energy physics in the future is very bright. So many exciting projects ongoing, and so many fundamental questions we need to answer. And the future collider will be the tools, opportunities for us to shoot at, and it's indispensable. Thank you.
Probably one or two questions for Tao Han.
Okay, thanks for your talk. I'm curious to know about your idea about the quantum gravity proposals about the standard model and naturalness, for example. They mentioned that the standard model is the effective field theory and you are decoupling the IR from UV, but it is necessary to consider this UV IR coupling. What do you think about it?
Actually, I'm not exactly sure which direction you are asking for, but certainly I can try to make connection with gravity. As we know that gravitational waves have been observed in certain experiments. Now we have two classes already, right? One is the LIGO, one is a nanograv. So the gravitational wave, I don't know what John is going to say, that he's involved with some next generation direct measurements. Gravitational waves will be something like neutrino, but even better. Neutrinos are propagating very far neutral, but gravitational wave carry information all the way from the early universe. And therefore, gravitational wave signatures may be connected to our fundamental physics. But that's not about the quantum gravity. So that's not about the quantum gravity. This is really the gravitational wave, the complementarity to help us to understand the higher scale physics. But quantum gravity, from my viewpoint, I think there's only two possible aspects. One is the quantum gravity probably have some imprint in the inflation at the very, very early universe. It may be at inflation and the beginning of Big Bang, then the gravity is at a very high energy quantized. The quantum gravity may have information from there to carry on. We may learn something on that direction. So that's the only place I can think of quantum gravity may come in. The other place will be the new formulation in theory, like active dimensions. If you have active dimensions beyond our normal one, gravity propagates everywhere, you search for active dimensions, suddenly you probe into the gravity aspect. I think this the large active dimension is the other place. You have a non-ambiguous identification for gravity and gravitons. You can even look for the closer Klein gravitons. So then there are certain aspects, but
okay, thanks.
Yeah.
Okay, any more questions? We have expert here, right? So also have a fact.
Microphone.
Right, so compact linear collider, how many stages do we have to increase to the energy to 70 eV?
You mean click?
Yeah, clean.
How many stages?
Yeah, yes.
I'm not sure it's a fixed, but certainly people have the idea to start from 350 GeV around top quark and shooting at the 1 TeV. Eventually, we may be able to reach 3 TeV. So these top quark threshold around and all the way to 3 TeV is our current understanding. I defer this to the authoritative answer to Christoph, and he has been one of the drivers. Do you have some comments to compliment about the state? I don't exactly know what the state. You mean how many?
So it's gradually increasing the
Okay. Yeah, that's what I meant. Click. So three stages, and similar to what I said, starting from TeV threshold, ending at around 3 TeV, maybe somewhere between 1 TeV-ish. So that's the current planning, maybe even documented already.
So the purpose of Planck is aimed for the Higgs boson interact with other particles, or maybe itself, right?
Self-interaction, yes.
Yeah.
Yeah, the triple coupling is the clear indication that's a self-coupling, yeah. I think click certainly can contribute. Click may not be the best place, but 350 GeV is his factory. It is his factory, but not optimal. It's not too much smaller than the threshold. Yeah, click can serve as a his factory, for sure, but not the optimal energy, but certainly can do.
Okay, so let me end one small question. So you mentioned the muon collider. So suppose either CEPC or FCCE is going to build, then what is the timeline for muon collider?
I don't think that's there's any interference among, and my thinking is people should all try to develop the technology and as fast as we can, and there's no guarantee that anyone probably will be built, and there's no guarantee that if you build one, you would exclude the other. So I think there's none of them. From my viewpoint, there's no interference. I don't think there's even need an interference between CEPC and FCCE.
So what would you expect, like 10 years later or 20 years? I mean, right now, the Higgs factory, the CPC, FCCE is like within a few years, 3 to 5 years.
So everything is in flux, right? So then there's a different aspect. And I think in terms of technology, and muon collider is, of course, the least mature. So this technologically is the least mature for sure. But there are many other factors that's equally difficult. Does not mean that look at ILC. ILC is most mature. If you have the money, you have the gut, you can start constructing this in next year. But it may not happen. But there's other difficulty factors. So just simply looking at this technological challenge, it may not be the full measure for the success. So I don't think it should be interference with each other. And the CEPC go full speed. We should be supportive. And the FCC go full speed. If we're able to do that, it's wonderful. Anyone is materialized. It's a tremendous advancement for our understanding of nature, for our field.
Any more questions? Okay, so if no more question, let's thank Tao Han for this excellent overview talk again.
Thank you. Thank
We
you,
will
Hong
come
Jian.
back by 45, less than 10 minutes.